speaker today is Prof. Schick from Göttingen, and he's talking about geometric model for 3C K-homology.
Yeah, thanks. Thank you to the organizers for having me here. I registered late. I still was allowed to come, even to speak. I don't know whether I fit in. So it's a program on C-star algebras, subfactors, and applications. So C-star algebras maybe come up, subfactors and maybe not, applications you decide. And this week is on subfactors. So once again, we'll see higher geometry, higher twists, and almost Calabi-Yau algebras. No Calabi-Yaus, I'm afraid. Geometry and twists, you'll see. How high, you'll see. But higher is, well, relative, I guess. Okay, so once again, geometry to give you twisted. Oh, that was good, right? That is good. Okay, homology. Good. What is this all about? So let's talk about this twisted K-theory and homology. First. Okay, so we need these twists, and then we need these groups. So let me see. X is a space. A really nice space, like a manifold or CW complex, or just maybe just a topological space in the end. I'm a topologist at upbringing, so allowed to talk about topological spaces. And what we want to get is this twisted K-theory of X. And well, to twist, we need a twist on top of well, the information we have here, X space, how a twist. And well, given the space and given the twist, we should be able to define and discuss this twisted K-theory. Okay, so we have to settle what we mean by twists, I guess, on top of the rest, what this twisted K-theory is, and just to well, to complete the picture, I'm also going to talk about the dual theory to K-theory, which is K-homology, and again, I want to look at this twisted version of K-homology. So they should somehow come in pairs here. Okay, which means, before I want to talk about that, I want to talk about that. That was my plan. What are twists? And indeed, this should be an assignment. So that's the question. And the answer is factorial assignment so 2x, we assign these twists on x. And if I say factorial, I should maybe also say that this is covariant. So we can pull back these twists along maps between spaces. And what should these twists be? Well, twists should be well, I guess the fancy word would be groupoid. Which is additional pointed and down to earth. So what's a down to earth version? It means we have a set, maybe like that, twists of x, or twists for x, together with isomorphisms between twists, which is what a groupoid is after all. Together with, for any two twists, a set of isomorphisms tau 1 to tau 2. Okay. And functorial assignment means if I have a map between spaces, I can pull back the whole business. So the set of twists as well as the isomorphism between those. Okay, that is what twists are for me. And well, pointed means there's a special twist. It should be the trivial twist. Trivial. Okay. Each time you insert the trivial twist up there, you get the usual theory. So untwisted K-theory. That is the idea of this trivial twist. So that you have an extension of what we know, K-theory, to a more general situation. But that was abstract. Let me give you two examples we're going to use. The first one is that twists on X should be the same as was defined to be. I'm giving you now the objects of this thing. So I set almost a set bundles. P to X the following. So these are locally trivial bundles with fiber C star algebras. So it's a bundle of algebras, C star algebras. And all these C star algebras should be isomorphic to compact operators on your favorite Hilbert space. So we're in the L2 setting. And the isomorphisms between those are just the bundle isomorphisms in the usual sense. So fiber-wise isomorphism of C star algebras. Why did I put down this example? You see, it's not quite a set here because it's probably objects of a category. But let's not worry about this too much. We, in this case, have a observation we can make.
Sorry, this is supposed to be contravariant, is that right?
Yeah, you pull back bundles.
Sorry?
You can pull back bundles.
Yeah, I do a covariant up there.
Oh, I wanted to say contravariant. Sorry, this is a contravariant function.
Yes, all right.
Uli should have. Good. Observe the structure group of such bundles. This is going to be the automorphisms of the fibers. And what are the automorphisms of compact operators on the separate Hilbert space? This is the projective unitary group. Automorphisms as C star algebras of K of H. This is what I would call H. H is this little L2. That's PU of H, which is the unitary group, which is contractible modulo its center U1. Okay? So these are precisely the automorphisms of the fibers, and that is then the structure group of such bundles. From that, you can get that isomorphism classes of these bundles are in bijection to homotopy classes of maps from the space. So the space should not be just nice enough for this to hold, to the classifying space for this group. PU. That's a general fact about bundles of this kind. The isomorphism class of these bundles are classified by the homotopy class of maps to the classifying space. That's what classifying space means. Synonymous. And inspired by this, let me give you a second example for what twists could be. Example 2 would be, so maybe just in other words, tilde here of x. Well, you should observe that it's, and I did not say the twists are isomorphs in class of bundles. And it's very important that they're not. They're honest bundles. Otherwise, it doesn't make sense to talk about isomorphisms between them. If you should have an honest object, then you can talk about isomorphisms between two honest objects. So in the same way, my observation that these isomorphism classes are given by these homotopy class of maps, it's not the homotopy class of maps which can be twists if you want to talk about maps in some sense, but we have to improve this to some concrete objects, more concrete objects, and that's what I'm doing here. It's just a set of continuous maps from X to a fixed model for this classifying space for this projective unity group. And now, by definition, the isomorphisms in this twisted model, in this tilde model of two of these maps, F1, F2, I'm defining to be homotopies from one to the other. Homotopy from F1 to 2. Well, and those I want to take up to homotopy of homotopies. And again, you can see this satisfies my conditions. It gives me for each space a certain set. It can pull back now, but just pre-composition, and we have, well, a certain set of isomorphisms, and we use homotopies. You compose those things by just concatenating homotopies. And I do it up to homotopy so that this is how you concatenate. Okay, so two ways to define twists, and you can also see that we can go from 2 to 1. To F, assign the pullback of the universal bundle. This is a classifying space, so I have the universal bundle of the kind we are interested in above it, and we can just pull back this universal bundle with our map F to get a concrete element in the other twist. Okay? But I actually do not know how to map easily from 1 to 2 without choices in a canonical way. Okay, so
What is the base point in the second model?
constant map, so maybe you should fix a base point in your BPU to be very precise here. Yeah. But constant map is what I want. And trivial bundle is, of course, a base point in the picture where the twists are bundles. Okay, so these are twists, and I don't know how high they are, but this is for me twists are. So
maybe you want isomorphisms after homotopy? Otherwise, I mean, you cannot lift the homotopy uniquely. I think you want isomorphisms.
You mean it for maps between them, where you put it?
Or the
Maybe write down
morphisms.
what the isomorphisms of bundles are. But I think I want isomorphisms. Maybe up to homotopy. Okay, so let me quickly, although that's not the theme, define the twisted K-theory, where I now use as a twist one of these P's, which is one of these bundles where the fiber is compact operators on the Hilbert space, but not canonically isomorphic compact operators of X. Well, that is fortunately very straightforward to be done. Let me do it if X is compact. So we do expect that K-theory is related to operator algebra, to C-star algebras, and there is almost immediately the C-star algebra we need around. We take the algebra of sections, continuous sections of the bundle P. Because the fibers are C-star algebras, this whole thing will be a C-star algebra where all the operation is done pointwise. And so we have a C-star algebra of sections now, and the K-theory of the space twisted by this P is just the K-theory of the C-star algebra. So you can check the operator algebra part. Talk about operator algebras now. Very well. So now let me move to K-homology.
You really want to start down? Do you have a star up or down on that? Or
Once again,
the star on the second K. Does that have an up or down or not really?
well, I guess the usual convention is that K-theory of C-star algebra, which is covariant in C-star algebras, is marked with the star downstairs, and that is the K-theory of space, because we have a contrarian assignment from spaces to algebras. So I think it's consistent with what people usually do.
We're using the K-homology of C-star algebras with the star up.
Yeah, this is just a entirely typographical question.
Yeah, sure.
No.
But I mean, it's really the K-theory. So in this very basic setting, K0 is projectors or idempotents up to equivalence in matrix algebras over these. Actually, we don't have to take matrix algebra because it's a stable algebra. And K1 is unitaries up to equivalence. So that's what I'm talking about here. Okay. So K-theory is a generalized cohomology theory. In the sense of algebraic topology satisfying the Eilenberg-Steenrod axioms. So homotopy theorists tell us there is a dual K-homology. It's for spaces, we also have it for C-star algebras. So that's a sort of general and abstract machine, but indeed there are quite a few geometric models for K-homology. And what my goal is to explain how we can twist K-homology the same way we can twist K-theory, so how this can be done, and then show or discuss how these geometric models for K-homology extend to twisted case. So maybe a word of order why this might be worthwhile doing. We try to do two motivations for why we'd like to do that. So actually the motivation is rather for why K twisted in the first place. and then maybe along the way also by geometric models. Okay, motivation 1 is orientation and Poincare duality. And there's a very classical thing I want to start with. If M is compact, m-dimensional manifold, no boundary, and oriented in the usual sense, we all know, then of course we have a fundamental class in the top, which is here dimension degree m, homology of the manifold with integer coefficients, and using it we get a Poincare duality isomorphism between the cohomology with integer coefficients and the dual homology. So far, so good. Now, you might wonder, what if the manifold is not oriented? So, of course, the statement as stated here does not hold anymore, but twisted homology comes to rest here. There is a twisted versions. Ordinary homology and cohomology. There is, shorten this, for any m, for all m closed, meaning compact, no boundary, canonical, and orientation twist. We call this O, among those twists which we use for twisted homology, which look different to whatever I've done for K-theory, with a fundamental class, always exists, and is actually canonically given in homology if we twist by this orientation twist. That's with integer coefficients that we previously had that. And we also have Poincare duality between ordinary cohomology and twisted homology. So the twisted versions kind of cure the problem that we don't have orientability. Let me make one more remark. This is class which is always there. How about picking an orientation as we're used to in classical, well, talking about orientations or manifolds? Picking an orientation is possible only if this orientation twist, which is canonically there, is isomorphic to the trivial twist. It corresponds, picking an orientation on the manifold, then corresponds to picking an isomorphism between this canonically given orientation twist and the trivial twist, which is our base point in the set of all twists. So this is also kind of encoding this business of twists, the idea of usual orientation. And now, if we talk about K-theory, the question is, want the same for K-theory K-homology, which is one of the motivations why this kind of twists are an interesting issue. It will also allow us, I don't want to write things down in that detail, to define integration over the fiber maps in greater generality than we have it here, because we can again cure problems by introducing and using these twists. Okay, so that's one of the motivations why using twisted theory is interesting. And a second motivation is ring theory applications use twisted K-homology, K-theory to classify certain charges in the presence of background. Papers by Witten, Fried, Moore. I don't really understand what's happening, but there are applications where twists certainly are used. So you now have the applications checked as well. But certainly not anything I want to go into details here. Okay, so let me put in a buzzword. E-brains and their charges. E-brains coming up later, because maybe that's giving me one further reason to look for geometric models of this twisted K-homology. These E-brains are certain manifolds floating around in space-time, and they are certainly very geometric objects, and you want to describe K-homology using such kind of geometric objects. At least that's one motivation I learned from these semi-physics papers, to look for geometric models of twisted K-theory and twisted K-homology. Okay, so motivation discussed. I putting up a strong statement here, I guess. Indeed, there are many geometric models for K-homology. Let's look at this statement. So I want to make this a bit more precise. Motivation is motivated. So, yeah, of course, this is a matter of taste or definition. What is a geometric model for a homology theory? Let me show you one example of a geometric homology theory. Geometric homology theories. Baby one would be singular homology, and I mean by geometric that there is a model given by cycles. And what are the cycles? The cycles come from maps from a simplex to the space X. Okay. So these are nice geometric objects. You just have simplices somehow in your space X. Of course, not all maps of that kind of cycles. You have to look at the right ones and combinations. But this is a geometric model. We can probe our space, but with geometric objects inside it. A second version of that would be that instead of probing the space with a simplex, we probe it with other nice objects, and the next nice object, maybe, or even nicer, are manifolds. So let's probe the space with manifolds. That's giving rise to Bourdism. omega of x n here. What is the Bordism group of the space X? Defined to be selection. We have the set quotation marks of all maps from n-dimensional closed manifolds to X. So it's a closed manifold. So these are the cycles, as we have cycles of that kind here. They are closed, so they are all cycles. Don't have to put extra conditions on that. And the equivalence relation is Bordism. So here is M1, U1 mapping to X. Somewhere else is M2, U2 to X. And when are two such considered the same? There is a W manifold one dimension bigger, whose boundary is M1 minus M2, and the map has to extend to the whole Bordism. Okay. Now this is a covariant functor, but just post-composing with a map from X to Y. So, yes, most of you have seen that. This is a nice geometric homology theory, and even better, there's not just one, there's a whole huge family of such, decorated by typically group G, which is what type of manifold with what kind of structure you're looking at. Which just explain that in example. More motivation to go away. So G refers to extra structure put on M, and if you put it on M, you will also put it on W in the Bordisms. So G equals O means no extra structure. Unoriented Bordism, we call that. G equals SO means orientation. So we put an orientation on the manifolds and the Bordisms, and on the Bordisms in a compatible way, strict to the orientation on the boundary. And there are more versions. G equals U means we put a stably almost complex structure on the tangent bundle. And there's one more I want to cite here, which is spin C. And I guess I don't want to discuss that too much. It's a refinement of orientation through changing the structure group to the spin C group. Well, okay, so quite a few geometric homology theories, of course, I've proved that the homology theories can be obtained that way. And so none of them is K-theory or K-homology, which is what I promised to give you. So let me give you K-homology now. K-homology from Bordism. First one. Yeah, Connor and Floyd show the following. We want to get K-homology of our space X in a geometric way, and getting it in a geometric way means for them, the canonical isomorphism here, to start with Bordism of the right kind. And it turns out that K-theory is, of course, also geometrically given by complex vector bundles. So maybe it's reasonable to expect that complex or almost complex Bordism can help you. And that's precisely what they're saying. You take this group here, but then you have to put a new additional equivalence relation on it. This can be expressed like that. You tensor this thing over the unitary Bordism of a point. And you see that this is a ring because we can just take the Cartesian product of two manifolds. That defines a ring structure on Bordism of a point, and Bordism of another space, the module for that ring, because we can take the product of one manifold with a map to X with another manifold with no map, because it's for the point. Okay, so a module for that ring. And there's another module for that ring, which is the K-homology or K-theory of a point. So there's a canonical ring map from this ring to that ring, which is complex orientation, and we can take this tensor product and get the K-homology of X. This is a surprising result, because if you look at this ring, it's a complicated object, and this module for that ring has no reason whatsoever, and actually in general is not flat or anything like that. So tensoring something over this ring with this particular module is not likely to preserve any kind of exact sequences. It's not an exact functor in general. But it has to, because all the exact sequences we have in homology theories, like the Myrick-Torres sequence, somehow have to be preserved because they're holding here. That's also homology theory. So a miracle happens here for this special modules that are showing up here, the special Myrick-Torres exact sequences show up here. It is exact, although it's not exact in complete generality. Now, another version of that same thing. They had a different reason for wanting to do what they did, but one reason I want to mention is that K-orientability. In the motivation I raised, we talked about orientations. Orientability for K-theory and K-homology is equivalent to having one of these ominous spin C structures. So it would make much more sense, because that is somehow the word where K-orientability works, that instead of using unitary Bordism, which is a very strict restriction, not too many manifolds make cycles for unitary Bordism, to work with spin C manifolds, because they are somehow really in the world of K-theory and K-homology. And Hovey showed that this works. So the same statement we have here works also for spin C Bordism, just with the same formula. So again, we can tensor now the spin C Bordism over spin C of a point with K of a point, and we get canonical isomorphism, K-homology of X. This also works for real K-homology, which is what Hopkins and Hovey really were after, I think. Let us stop here at that point. And a third model I want to give you, which is in some sense also from Bordism, but in a slightly different way. Is Baum Douglas cycle model. So what that is, does it say K-homology of X is obtained from cycles, which are pretty much cycles of this kind. So we have M, which is a closed spin C manifold, so it has a spin C structure as before. We have a map, call it U, as before, to X. And on top of that, we have an object E, which is a complex vector bundle on X or an element in the K-theory of X, so that you could play with either or the other. Both gives you, in the end, the same group. Okay, these are the cycles, and then we have to mod out an equivalence relation. So you can see this kind of construction starts with spin C manifolds with a map to X, exactly like there, but we don't have this extra information of a bundle here. And we have then to put another equivalence relation. I mean, this tensor product really means we take these things and a certain equivalence relation on it. It's not always so easy to describe. As you know, when working with tensor products, getting explicitly who is equivalent to whom is not so easy to decide. Okay, what is the equivalence relation here? Generated by, well, first maybe isomorphism, and the obvious way to make this a set. Then Wardism. Well, we know what Wardism means. I drew a picture. Now we have a bundle on top, so the bundle has to extend over the Wardism to make two things equivalent. And then there's something which says direct sum of bundles corresponds or is equivalent to the disjoint union of spaces. So just take the disjoint union of two copies of the same M. Another.
You want the bundle to be on M rather than X?
Huh?
Is the bundle supposed to be on M or on X?
That is on M. Okay. Thanks a lot. Yeah. And in our D.
Now I'm happier, yes.
Yeah, thank you, thank you. Pay more attention. And the fourth one is, maybe I'll call about that a bit later, called vector bundle modification. For the time being, let me just state that it allows to pass from an m-dimensional manifold to an m+2 dimensional manifold. After all, K-theory and K-homology is two-periodic, and so far we would have seen a dimension invariant here, which would make it unlikely to be two-periodic. But the vector bundle modification just takes care of this quadradicity. So it's built in by this equivalence, this part of the equivalence relation. Well, okay, so that's an established result. 3 results, and I guess what I would want to be able to say is that they just hold more or less the same way for twisted K-homology. Okay, so this is now the theorem. What I'm after, together with for Baum, maybe Korami, Joachim. Number this is B, and this is C. The other one is A. Twisted versions of B and C are true. Okay, so to be able to formulate that, I maybe should tell you what twisted spin C Wardism is and what these twisted versions of these Baum-Douglas cycles are. And then you could take, as a definition of twisted K-homology, the result that this is true of the left-hand side. Okay? So, for that, need twisted spin C Wardism. this is easy enough. So given M, eventually with a map to our space B Pu of H. We will fix this space once and for all, and we will go to the second version of twists. So twists are maps to this particular topological space B Pu of H. Is otherwise also known as a classifying space for third integral cohomology. So it's a well-known object. And this map here will come about as a map. So what we really care about is our space X. We define some theory of X, and the X has to come with a twist, and the twist was this map to BPU. Once again, this is the twist. And if you want to talk about twisted spin C Bordism, we will talk about manifolds with a map to X. I mean, that's what gets into defining Bordism, right? It's manifold with maps to X, U, that kind. And of course, if you have a map to X from M and then a map from X to BPU, you can just compose and you get a map from M to BPU of H. Okay. And given such a situation, a map from M to BPU of H, is a notion of U first composed with F twisted spin C structure on F. And maybe, so this is just connected to bundle theory on M and classifying maps for bundles. Maybe I'm skipping it over. So just this is a detail similar to the detail I skipped over to say precisely what a spin C structure is. So there is a geometric way to define twisted spin C structures once you have a fixed model for the space BPU of H and a fixed map to it. Let me clarify if F composed with U is a constant map. And we talked about choosing a base point before, just a constant map value this base point. This comes down precisely to spin C structure on Tn. So, as we should expect, for the constant map, this twisted business is just the ordinary untwisted business. Okay? And well, with this information, there is also restriction of twisted spin C structure to the boundary in case the manifold would be a manifold with boundary. And so we have all the ingredients. We need to just copy the definition of Bordism, but now for twisted Bordism. So if we have this map from X to BPU of H fixed, our group, our Bordism group, will be the M's with maps to U with twisted spin C structures in this sense, which I didn't quite describe. It's the omega spin C of X, but now twisted by this map F. So twisted spin C structures, manifolds with map to X with twisted spin C structures, so just case sense just described, modulo Bordism. So we have a nice way to define this fully geometrically, and somehow it seems that some of the string theorists like to think of these maps as D-branes in a setting where you have X, your space-time manifold, with a background field described by this map F. Okay. We need to be a bit generous with this background field. Anyway, so these are kind of these C fields around. Now observe that, or maybe that's another bit of information, we can still take the Cartesian product with an honest spin C manifold, with any one of these guys, and get a new twisted spin C manifold. Okay, so this here is exactly as it was before, a module for the ring spin C Bordism without any twists of a point. Cartesian product makes this twisted, so that's where it's important, this twisted spin C Bordism over X module for spin C Bordism of the point, and that way the formula makes sense. But I mean, we can take this left-hand side tensor product, and we can hope that it canonically gives the twisted K-homology of X. And the theorem I wrote down says precisely this works. So, and for the sake of saving time, I don't give you the official definition of the K-homology twisted of X, but indeed it is exactly what you get. So if you like, you could take this as a definition of twisted K-homology. Now, nice geometric model, one kind of D-brane model for twisted K-homology. And now we can also guess how to modify the Baum-Douglas cycle model. That's pretty straightforward, I guess. Where we used closed spin C manifolds before, we just learned we might as well look at twisted spin C structures on M. And that's what we do. So the twisted Baum-Douglas cycle model uses MUEs, where the M comes with a twisted, in a sense, just described spin C structure. Otherwise, everything is unchanged. And of course, in the equivalence relation, you have to check what you want to do. And the Bordisms is now Bordisms with the Bordism has a twisted spin C structure. The vector bundle modification is the same vector bundle modification as before, with honest spin C vector bundles. Otherwise, you wouldn't get the same kind of twisted structure after the modification. And again, the statement is that this twisted Baum-Douglas cycle model gives you what you want to get, the twisted K-homology of X.
Can you put the twist also in the K-theory class? I mean, if you don't work with bundles, does this, I mean, you already wrote that K is naught of M. Could you just take their twisted class and then untwisted?
So let me, I have 2 minutes. We comment on this business here a little bit. So, as Uli pointed out, or my choice was, and that is going back to a paper of Baum, Carey, and Wang, and another paper of Wang, put all the twists in the manifold. And it seems that some of the physics literature likes to do that, put the twist all in the manifold. And it's actually hard to work out that this gives you what you want to get, twisted K-homology. The ways how to prove this Baum-Douglas cycle model, that it's the right thing, just break down. Now, we had to find a new way to prove that. I go through the other result, through this twisted Hopkins-Fourier result. You could also take ordinary, usual spin C manifolds, then you would have to use not vector bundles, but twisted K-theory classes. And that does work. Baum, Carey, and Wang proved it, and the usual proof actually goes through. So it's easier if you have this twist on this end. And there's a third option. You could kind of split the twist, put part of the twist on M, part of the twist on E, have a most kind of encompassing model where you have many, many cycles. That also works. It is hardest to restrict to the twist only to have it on M. Well, I guess there is not enough time to tell you how this is proved. So maybe I just stop now. Question?
So there's another version if you just take the K-homology of the operator algebra.
That works too, yeah.
And in the twisted case, where this also agrees with that?
Yes.
By the same maps using Dirac?
Yes.
I don't think so. That will, I mean, only for compact X. Yeah.
I agree. Compact X. Otherwise, you have to be a bit careful. But then the big question is somehow to show that what you define has these Maya-Vittorius sequences, which you can do with that model, and it is hard to show with these tensor product models. That's somehow the big issue. But once you know it, you check that the theories coincide for the point, and then you also have to construct the transformation, but you already gave it, and then it's kind of standard fare to get that's an isomorphism, at least for CW complexes.
Okay, I was going to ask questions, one of which just got asked. But the other one is, so I mean, this is a particular example of twists, and I guess you could replace compact operators by more or less anything else, and then there could be all kinds of other things. But in particular, suppose you use the compact operators censored with a strongly self-absorbing C-star algebra, the sort of way that Darbat and Penny have done.
Yeah, I mean, this will come back, and this talk should have been a talk for Thursday, because we have a whole series of twisted K-theory and K-homology talks. That gives you the option to have much more general twists. So homotopy theorists would have told you that this is only a very small fraction of what possible twists. So the compact operators in Hilbert space have as automorphism group PU, but everything comes back down to homotopy theory, comes down to these classifying spaces for K-theory, the spectra in the homotopy theory world, and then you would have to look at automorphism of the spectra, GL1 of the spectrum. That's a huge thing, and we just look at the tiny part of it. And the model by Marius and Ulrich just allows you to look at much more of the twists from this operator theory point of view. I think that's right. So you will hear about that right on there somehow, right? Yeah. So
And it also sounds like you could define for an arbitrary contravariant functor from spaces to suitable groupoids. You could, in principle, construct something, and although maybe for arbitrarily chosen functors, you can't say much.
right. I would not know how to twist something like spin C Bordism with these more general twists. So the kind of result I didn't even write down. So I mean, the twist here and the twist here, and still true, requires me to find a way to twist Bordism, which the more general the twists are, the more difficult it is. I wouldn't know how to do it, so I couldn't formulate the theorem you're looking for. My geometric model works for these kind of twists. I mean, of course, there are guys which are around which should try to generalize it, but I don't know right away how to do it. It's a good question, but I don't have an answer to it.
Other question? Then it's time to speak again.